in this lecture, I'm going to describe how to calculate the escape velocity from a planetary body. There's two ways to do that. There's the traditional Newtonian way, and in the pi-space theory, there's the equivalent way to do it. It produces the same values, but I will describe the Newtonian way in parallel with the pi-space way of doing it, and to show at the end of the lecture some calculations and some math. But initially, I'll just talk about the theory of what is potential energy first off. So in this case here, you see a pi shell, as it's called, a sphere or an atom, in other words. It could be a planet or it could be just an atom, and you see that the distance s here is proportional to the area change. So in the pi space theory, potential energy maps quite simply to the area gain as you move up in a gravity field, and kinetic energy relates to the the area loss. So when we talk about potential energy, we're talking about the change in the area of an atom with respect to an observer. So if we want to get off the planet Earth, we have to calculate the amount of area change required from the planet, the base of the planet, to the outer edge of the planet. But first we have to understand what is actually potential energy. And in this case, potential energy in the pi space theory is just a change in area. So we have to sum up all this area change here, and we then have to convert that into a corresponding velocity. Now, the pi space theory is pretty simple. If you have an area and you want to get back to a diameter line, which is what maps to velocity, you have to square velocity to get to an area change. So that's the simple mapping between a velocity and an area change, v squared. So let's take a look at the formula that traditionally Newton produced for potential energy. It's a very straightforward formula. The potential energy is m times g times h. That's the mass m, which is the mass inside the one or more atoms, or pi shells as I call them, and then g is the area change with respect to movement away from or towards the center of gravity. In this case, it's potential energy, so you're moving away from the object, so it's a gain in area. And h is the height h, typically in meters. So typically the way we understand gravity is it's meters per second squared. In another lecture, I've described why s is proportional, which is distance, is proportional to t squared, and it's because the time is proportional to the diameter line, or the diameter change of a pi shell, and s or h in this case, in this formula, is proportional to the area change. So the height that you move, the distance you move, is proportional to area change. If you move straight up, the area change is directly proportional to the distance. So that's why you can multiply it simply by g times h. Now, in pi space, the units are more explicitly called out, a little bit like in general relativity. G is g over c squared. So in pi space, g is typically described in terms of 0 to 1, and g and the units are c squared. So g is units of area. Okay, so in a very simple sense, is how to understand potential energy. You move up the pi shells, the gain area relative to the observer, the stationary observer. You can use the Newtonian formula, m times g times h, and you can imagine going right the way up to the top of a planet, and you have to sum it up. So let's just delve into some of the math behind that idea. In this case here, in pi space, this is the pi space formulas here. This is the general solution to potential energy. So we have m times g times h, basically representing the amount of area gain. So let's take a look at that idea in pi space. On the left hand side here we've g times h over c squared. We ignore the mass m because it's a constant for the purposes of this discussion. You could potentially imagine this formula having m times g times h over c squared equals m times 1 minus the cos of arc sine v over c, but we drop the mass on both sides. So what we have on the left hand side is the area gain, which is g times h over c squared, equaling the area loss. And this is a formula that has been derived in other lectures. This is the equivalent of the kinetic energy formula in Newtonian world, which is better known as the half mv squared formula. So this is the pi space equivalent of those formulas. If you're not sure how I derived these formulas, I have other lectures, but for the purposes of this lecture I'm going to describe escape velocity. So let's take a look at the area gain equals the area loss, which is what this formula represents. So then we move on to saying we want to solve for an escape velocity. Okay, so it's not just a case of putting one against the other. So we're going to solve for kinetic energy equals potential energy for V over C, and for where V is less than C and V is less than V is less than or C. What I mean by that is that the idea of the pi space formulas is, unlike the Newtonian formulas, they work with very large velocities. This is one of the reasons why you might want to use pi space, in that they give you theoretically accurate results where velocity is almost at the speed of light. So let's just work through an example here where we want to redevelop these formulas so that we get a velocity based solution. So in other words, if we know potential energy, what is the velocity equivalent, right? So let's take a look at the formula I just showed you. We've g over h, gh over c squared is equal to 1 minus cos arc sine v over c. Now what we're trying to do is solve for velocity v. So essentially what we do is we gradually change the formula so that we are getting the v out of the formula. So we multiply the solution and we get an arc cos equals arc sine expression, and then finally we get the velocity base equivalent formula, which gives us the potential energy in here. This is the potential energy part of the formula. This is the potential energy part of the formula here, and the g times h part over c squared. So this is the g times h over c squared part, and this is basically the potential energy. So if we know this potential energy, which is the gravitational constant and the height, this is the velocity that we get back. Now you can use Mathematica to plot the results. In the case of I'm talking about here, we start at 0, 0, and we go 1.0, and we have steps of 0.1. That's what this means. So we know g times h, and in this case, these are the values that we get back. All right, these are the values that we get back. Now, if you look closely at the next table, which uses the square root of 2 times g times h, if you're familiar with the Newtonian work, if you want to get a velocity from knowing the gravity and the height, you just put in, you square root 2 times g times h, and that's how you get it. So if you look at the results, they're pretty much the same for low values of v over c, or g times h I should say. So they're pretty close. So these, then we put these in the comparison tables, and we get the pi space velocity versions and the Newtonian velocity versions. Now these are very, very high values, 0.1 of the speed of light. In other words, g times h over c squared is 0.1. That would be a pretty massive object. So using this formula, it's possible to work towards a collapsar, such as a black hole, using this formula. If you notice at the Newtonian velocity, when you put in a complete compression of the object, which is basically a black hole, the value that the Newtonian formula gives you is actually 1.4 times the speed of light, which is incorrect, as we know from the Einstein work. But if you look at the pi space velocity version, you get 1.0, which is speed of light. So when you have complete compression, you get the speed of light. You get coming back when something is completely compressed. So let's take this formula and do what the Newton did, which is basically that he put the kinetic energy equals to the potential energy. In this case, it's the gravitational potential of the planet, which is minus g times m over r. So let's just take that same example, and we have a formula for the kinetic energy, which is 1 minus the cos of arc sine v over c, and we assign the area loss to the area gain, which is the total. This is the total area gain for a planet. This is the well-known Newtonian formula, right? So we're going to solve this in the same way we did for potential energy, and the formula we get is the v over c is the sine of the arc cos 1 minus gmm over r. So gmm over r is the gravitational potential of two bodies or one body. So let's take an example of that, and let's take a look at an example of a planet. So for example, the Earth has a radius of 6,378 kilometers and 6,378 kilometers, and its mass in kilos is 5.98 by 10 to the 24. That's its mass. So we can then plug these values into this formula here, and we can get back what's called the escape velocity, right? So that's what this v over c is, right? So let's go down here, and let's take a look at the standard way of doing it for the Newtonian way of doing things. So in the Newtonian way of doing things, the escape velocity is 2 times gm over r, and you square root it. That's what the half is. And what you get approximately is 11.2 kilometers per second. More precisely, if you use Mathematica, you get 1183.7 meters per, I think that's that's meters per second. 11,183.7 meters per second. That's just to get out of the Earth's orbit, Earth's atmosphere in terms of its known radius. So let's take that same, let's use the pi space formula then, and do the same thing again. So we have two choices. We can use either the speed of light, or we can in terms of meters, or in terms of miles. So for the purposes of this document, I'll use the speed of the meters, because if you look at the example up here, we're doing everything in meters and kilometers. So we're going to use 299 million meters per second, 299,792,458 meters per second, right? So let's put that into this Mathematica expression. If you have Mathematica, this is a student edition. It's free. You can try it out. You just put this in. So what we have here is the sine of the arc cos. We have the distance in terms of meters. I think it is here. Yeah, meters. And then this is the mass, and then we divide it here. This is universal gravitational constant. And then this is the mass, and then this is the meters. Meters here, and then what we do here is we divide the gravitational value. What we do is we square the speed of light here. Okay, so in pi space, because we're dealing directly with the area change, we have to convert to the area here. So we have to square it. We have to divide it by c squared here. That's the equivalent of c squared. And then the final result, this is where it maybe gets a tiny bit tricky. We have to multiply that by c. So what we're trying to get back is the velocity. So like I said before, if you have an area and you want to get to an area calculation and you want to get to velocity, you multiply it by v. You don't multiply the c. You multiply it by c. You don't multiply it by c squared. So squaring the velocity gives you the area. So This, interestingly enough, gives us exactly an answer matching the the expression used by Newton up here, which is 1.1. And there are two different formulas. It's the square root of 2 times 6.67 and so on. The G, the big large G times mass m divided by the or here, which is the radius, and we have to divide that entire expression we have to divide that entire expression by c squared, because we're dealing with area, because that's the area change, right? So in this case they match, so they're very accurate. The pi space is very, very accurate in terms of coming up with the same values as 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 the Newtonian work for the smaller c values, and then theoretically it's completely accurate for going up to the speed of light. I can't measure a black hole, obviously for obvious reasons, but the theory points, it is correct with the Newtonian values at the lower values. Now, in terms of actually trying that stuff out yourself, you can just take a look at the formula here. You can take a look at the formula here, and you can just try it out here. So you can do this, and then you can use the formula, but just be careful with the c squared part, dividing by c squared, and then multiplying the result by c to get back to the velocity, to get to the Newtonian version. That's all implicit in the Newtonian work. Now, in terms of actually a piece of software that does this, in the pi space theory, there's a formulas page, which is off the pi space site, and there's the sample Java code. And in the sample Java code, which if you download it, if you click on it, it will give you a piece of code that you can actually run against the Java JDK. There's nothing special about it. So it's pretty standard code, and if you take a look at it here, at the very bottom, I have code here which creates a pi space object. This is the mass of the planet. This is the radius of the planet. The gravitational potential is generated, and then you solve for you get the gravitational potential, which is the total area, and then you solve for the Newtonian potential to velocity, or pi space. Now, when you run it, say for example in Eclipse, the answers that you get are the following. So pretty much it's the same values you get with the Newtonian work. So that's describing how to use the pi space theory to calculate the gravitational potential and the escape velocity. Thanks very much.